All right, let's talk about something we all use literally every single day as developers, strings. But have you ever really stopped to think about what they are? Under the hood? Well, today we're going to pull back that curtain and expose the incredibly powerful data structure that's been hiding in plain sight this whole time. Now, if you're like me or pretty much any developer out there, you've probably got this thought lodged in your brain. A string, well, it's just characters, right? A sequence, an array, a list. Super simple, case closed. Yeah? Well, that simple belief is completely 100% wrong. And look, if you care at all about performance, this is something you've gotta understand. The reality is way more interesting, and the implications, they're just massive. So if it's not just a list of characters, what in the world is it? A string is a highly specialized data structure. It's got its own very specific rulebook for how it handles memory, how it performs, and how it behaves. You really gotta think of it less like a simple box for characters and more like an engineering marvel. Okay, so to really get this, let's break it down. Let's look at the 3 core properties that make a string, well, a string. This is where all the magic really happens. First up, mutability. This one's a biggie, and the language like C++, a string is mutable. That means you can just go in and change a character right where it sits. Easy. But then you look at languages like Python or Java, and strings are immutable. Any little change you make, even adding a single character, doesn't change the original. Oh no, it creates a brand new string somewhere else in memory. And that difference right there, it completely changes how you have to think about your algorithms. All right, now we get to what I honestly believe is the most important property of all. Here it is. Strings occupy one single, continuous, unbroken block of memory. This isn't some random accident. It's a fundamental design choice. And if you want to understand string performance, this is the absolute key. So what's the trade-off? Well, because everything's laid out in one nice, neat row, accessing any character is that's just a fancy way of saying it's lightning fast. The CPU can do a tiny bit of math and jump directly to the memory address. It's instant. But, and this is a huge but, the downside is massive. Try to insert or delete something from the middle of the string. Ugh, it's painfully slow. Why? Because you have to take every single character after that point and shift it over one by one. Ugh. This all leads us to this really fascinating optimization. It's like C++'s secret performance weapon, especially when you're dealing with tons and tons of little strings. It's called small string optimization, or SSO for short. And it is brilliant for small strings. We're talking usually 15 characters or fewer. C++ does something super clever. It doesn't even bother with that slow process of allocating memory on the heap. Instead, it just stuffs the characters directly inside the string object itself. Think about that. It completely sidesteps one of the slowest things a program can do, allocating new memory. And the impact is, well, you can see it right here. It's just staggering. Look at this comparison with SSO. Making a copy of a small string is basically an OR1 operation. It's instantaneous. Without it, you're stuck paying that cost of allocating memory and copying every character every single time. For any app that uses a lot of strings, this is a total game changer. Okay, I know this might sound a little abstract, all this talk about stacks and heaps. So, you know what? Let's actually look under the hood. Let's visualize what's really going on with the memory. So here we go. You create a tiny string, say hello. That string object, it lives on the stack, and the characters themselves, HELL, they're not somewhere else, they are. Literally tucked right inside that object in a little buffer. What's missing here? The heap. There's no separate memory request. It's all in one place, totally self-contained, and unbelievably fast. This little trick only works for so long, though. The moment that string gets too big for its little internal buffer, that's when the switch flips. Only then does it finally go and pay that performance penalty. It has to ask for a new, bigger chunk of memory over on the heap and then copy all the old characters over. This is that tipping point where the performance of your string just completely changes. Okay, so with all this in mind, let's talk about something we've probably all struggled with. Why are string problems in coding interviews so freaking hard? You know, the ones on LeetCode or HackerRank? Well, I'm here to tell you it's not just you. There are some very deep, very real computer science reasons for it. I mean, these algorithms often force you to juggle all these complex pointer interactions. You have to understand deep concepts like periodicity, which is basically just finding hidden repeating patterns inside the string itself. And sometimes you even have to dip into really advanced topics like finite automata theory. You know, these abstract state machines built just for pattern matching. So you're not just playing with characters anymore. You're wrestling with some of the toughest concepts in all of computer science. And here is a classic trap. You might think creating a substring is a cheap, easy operation. It is not in C++. Every time you call S substring, you are creating a brand new string and copying K characters over. Now imagine you stick that inside a loop. Boom. Your algorithm that you thought was fast just exploded into quadratic time, and you might not even notice it. It is an absolute silent performance killer. But look, this stuff isn't just about you in a coding interview. These complex algorithms, these specialized data structures, they are the invisible engines running some of the most important tech we use every single day. Let's just look at a few examples. Take DNA sequencing. What is a genome really? Is just a gigantic string of A's, C's, T's, and G's. Scientists are using incredibly powerful string searching algorithms, things like KMP and advanced hashing, to find specific gene patterns to align different sequences. I mean, they're using string theory to literally unlock the secrets of life itself. Or how about search engines? Every single time you type something into that search bar, you are kicking off a whole cascade of sophisticated string operations. They're using these crazy data structures to power the indexing that finds your results, and that autocomplete that magically predicts what you're about to type on a fraction of a second. Malware scanning. Ever wonder how antivirus software can scan your entire hard drive, gigabytes of data so quickly? Well, they use mind-blowing algorithms like Aho-Cry. You can think of it like a supercharged search engine that can hunt for thousands of different malicious code signatures all at the same time in a single pass over your files. It's insane. And even something as simple as the diff tool you use in your terminal to compare two files. Yep, that's powered by the longest common subsequence algorithm. It's a classic dynamic programming problem that's all about strings, and it's what finds the smallest possible set of changes between those two files. And just to put the power of this into perspective, remember that malware scanner? Modern tools can efficiently search for over 100,000 different malicious patterns at the same time. That is the kind of mind-boggling efficiency you get when you deeply understand how these data structures work. So what's the big takeaway here? It's this. Strings are not simple. They are complex, highly tuned data structures. How they're laid out in memory is the #1 thing that determines their performance. Performance. And knowing this stuff isn't just academic. It's what powers some of the most critical technology that runs our world. So I'll just leave you with this one thought. The next time you search for a file or run a diff or even just type into a search bar, just take a second and think about it. What hidden string logic, what complex, beautiful algorithm is firing away under the hood, making it all seem so completely effortless?